Hello, and in this video, I will be reviewing the topic of electrochemical cells so that you can excel at them in AP Chemistry. To begin with, here are the basics. There are two types of electrochemical cells, voltaic or galvanic cells and electrolytic cells. Voltaic cells produce electrical current from a spontaneous reaction, whereas electrolytic cells consume electrical current to drive non-spontaneous reactions. In AP Chemistry, we will focus on voltaic cells mostly. This is a typical voltaic cell, and at first it looks complex, but after we break it down into its parts, it's quite simple. Firstly, we have the voltmeter, which measures the current output as electrons transfer between the electrodes. Next is the anode, which is our first electrode, where the oxidation reaction occurs and solid atoms are converted into ions and electrons. Here it is the zinc. Next is our second electrode, which is the cathode. Here is where the reduction reaction occurs and complete atoms are formed. Lastly, we have our salt bridge. And in the salt bridge, its purpose is to maintain the charge balance during the reaction. When looking at voltaic cells, you will use the equation delta G equals negative NFE to determine its spontaneity. G equals Gibbs free energy, which must be negative for the reaction to be spontaneous. N equals the number of moles of electrons. F is Faraday's constant, which is equal to 96,485 coulombs per mole of electrons. Lastly, E equals the cell potential, which is measured in volts. It is very important to note that for the reaction to be spontaneous, the cell potential must be positive. Mrs. Nielsen will provide you with the standard reduction potential sheet, as shown here, to make determining the cell potential of a voltaic cell easy to calculate. This table of values also allows you to determine which half cell is the anode and which is the cathode. For this problem, we are using zinc and copper at +2 charges. Let's try with this equation in blue, which shows solid zinc forming or getting reduced, and copper 2 ions forming or copper getting oxidized. For zinc getting reduced, the cell potential is negative 0.76 volts. And if the copper is oxidized, the cell potential is negative 0.34 volts. Well, you may think, oh, on the sheet it says positive, but since the values here on this table are given as reducing potentials, and the copper is oxidized, we must flip the sign, so it's negative rather than positive. Now, if we add this for the whole cell, we get negative 1.10, which does not work because E must be positive. Now let's try the reverse, where zinc is oxidized and copper is reduced. This time, the zinc potential value must be flipped because it is the one getting oxidized. Once we add the values for the whole cell, we get the final cell potential to be positive 0.42, which works out to be spontaneous. Using the previous calculations, we can determine which is the anode and which is the cathode. The oxidation reaction always occurs at the anode, and the reduction reaction always occurs at the cathode. Thus, the zinc electrode is the anode, and the copper electrode is the cathode. We can double check by taking the oxidation states, and zinc begins at 0 and ends at +2, meaning it lost 2 electrons. Using the oil of oil rig, which stands for oxidationist loss, this checks out. Copper begins at +2 and ends at 0, meaning it gained 2 electrons. Using the rig of oil rig, meaning reduction is gain, this also checks out. Now let's look at this on the cell. The oxidation is at the zinc anode, which will get smaller as the reaction proceeds. The electrons will move from the anode through the voltmeter and then to the copper cathode, seen by the yellow arrows here. This copper cathode will grow as the reaction proceeds. Notice that the reduction reaction occurs at the cathode. Lastly, we have the ever-important salt bridge, which is vital for electrochemical cells to function. For our example salt bridge, we will use potassium nitrate, or KNO3. KNO3 will split into the cation K+, and the anion NO3-. The negative anions will move to the oxidation side, and the positive cations will move towards the reduction side. You should note that the cations move to the cathode and the anions move to the anode. Thank you, and those are the basics for you to be an expert on electrochemical cells.